So thank you very much for the introduction, and to organizers and the committees for this invitation. I am honored for. So I will lecture on the concept of torsion in algebraic groups especially, and problems which arise. And I will start with some generalities concerning the concept of torsion, and then turn to some more specific issues that I am more familiar with. So let me start with the etymology actually of torsion. When I heard this word mathematically for the first time, it was concerning curves in space, and somewhat torsion measures somewhat the twisting of curves in space. But in this lecture instead, I will consider the algebraic meaning, and the terminology came again from twisting concerning certain homology groups, but the algebraic meaning indeed concerns groups. Let me recall it. So an element, small g in a group, capital G, is said to be torsion if some power of the element, some non-zero power of the element is the identity. So it is very simple and natural concept. And such a power, any such power, is called an exponent for G. So such an element, a torsion element, generates what is called a finite cyclic group. And again, the etymology is because the powers, they repeat. When we arrive at the mth power, we find the identity, and then we find the G again, and G square, and so on. And the powers repeat cyclically. So we are reminded of a circle. This is a very vague intuition, but indeed it goes further than that, it goes deeper. And the circle comes into the picture beyond this vague intuition. This vague intuition holds in every abstract group when we have a torsion element, but we shall see that topology comes into the picture in specific cases. Now let me go to the context of algebraic groups where we shall meet this torsion. So what is an algebraic group? It is a group, but roughly speaking, it is a group where the points of this group are points in some affine or projective space. And the group law, what is important is that the group law is expressed by polynomials in the coordinates of these spaces. And let me say at once that we shall meet only commutative algebraic groups in this lecture. And this is important because in commutative algebraic group, the torsion elements form a subgroup, which is not true generally. Let me start by making the simplest examples of algebraic groups. And for simplicity, I take the points, the complex points of these algebraic groups. So we start with, for instance, the complex numbers. And the complex numbers is maybe thought as the set of complex points of the additive algebraic group, denoted GA. And this is very simple, actually. The GA is just the affine line as a variety, and the group law is just the sum, additive group. And here, over the complex, we have no torsion, because if we add an element a finite number of times and we find zero, the element must be zero originally. So in zero characteristic, we have no torsion in this case. So Let me go to the next example from the viewpoint of simplicity, which is the multiplicative algebraic group. And the points, the complex points of these algebraic groups are just the non-zero complex numbers. And the algebraic group GM, it is called usually. It is the affine line as a variety. It is just the affine line, but where we remove the origin. We don't want 0 when we multiply, of course. And now the group law is just the product. So very simple. These two are the simplest example, probably, of algebraic groups. Let me see now the torsion in this multiplicative case. In the additive, we had no torsion. In this case, we have very interesting torsion. The torsion elements are precisely the complex roots of unity. Of course, when we take some power, we obtain the identity, which is 1. And the roots of unity lie in the unit circle in the set of complex numbers, non-zero complex numbers. And how many of them? Of course, there are exactly m if we want an exponent m. So, and these form the vertices of the irregular m-gon. So how do we obtain these elements? We may think to go from the additive group, which has no torsion, to the multiplicative one by the exponential map homomorphism. And this is surjective onto the non-zero complex number. And there is a kernel. The kernel is just the homotopy group of the non-zero complex numbers from the viewpoint of topology. And the existence of this kernel, which is non-divisible, explains torsion elements. We may think in this way. And we find the roots of unity when the argument of the exponential homomorphism that I have written, e to the 2 pi I z, when z is rational, a rational number. And this provides a link with number theory, of course. So let me just to give an idea that the torsion elements are not something trivial, even in this simple context, even to decide whether a specific number, if I give you a number and I tell you this, let us see, is this a torsion or not? And this is already often a not completely trivial question. Let me make a very simple, just a very simple explicit instance, which someone will be able to answer instantly. But I think, for instance, a small challenge, is this number a root of unity? You see, this complex number is very explicit. It lies in the unit circle. So could be a root of unity, possibly, from this observation. And how to check? We can compute the powers. We can compute the powers. And if we obtain 1, we know that it is a root of unity. But if we do not obtain 1, we have to go on. And how to know how far we have to go on? This is the problem. So this is a very simple instance, but in general, such a kind of problem may be non-trivial, even to decide. So let me recall, Gauss already in 1801 was with the publication of Disquisitiones Arithmeticae, was the first to study in depth the properties arithmetical of the roots of unity. And as a corollary, he obtained criteria for constructing a regular anagon with a ruler and compass, which was an old famous problem, ancient problem of cyclotomy of the Greek mathematics, by no means trivial. For instance, it is possible to construct such a regular polygon for the values of n that you see displayed in the top row, but not for other values which you see in the second row. And the bold-faced number are the Fermat primes, which play a role in this business. I cannot recall, for time reasons, any exact statement, but this is already quite a deep and amusing, interesting problem. Gauss, already much before of the publication of the book, was able to construct the regular polygon with 17 sides, which is by no means trivial. You see a formula in the bottom for the cosine of this, and you see it is quite complicated and not trivial to achieve. Gauss, indeed, we may say that he anticipated the Galois theory of the fields generated by roots of unity, called cyclotomic fields. Galois theory did not exist, but Gauss already did this because he invented the periods, the invariants for the group action without calling a group. Of course, the concept did not even exist. And in this case, there are much more modern viewpoint by Tate, Grothendieck, and others. I see here there is a problem with, okay. The Galois group which arise may be seen as an algebraic manifestation of the monodromy group of the circle. So here the circle comes into the picture in a deep way. And algebraically, it is a geometric object, but algebraically, the monodromy group, we may see it algebraically, and it appears through the action of Galois group. How? We have the homotopy group of the circle is Z, and the homotopy group has finite quotients, which are the integers modulo n for the various integers n. And these quotients correspond to finite covers, unramified covers of the circle. And in turn, they correspond to homomorphisms from the circle to itself, given by the powering maps. And the powering map Z sends to Z to the n. The kernel is the group of nth roots of unity. And you see, we have the automorphism group of the covering group. Algebraically is just the group of integers coprime modulo n, but coprime with n. And this, so this is a topological object. In one way, we may see it as the automorphism group of the covering group, but we may, Gauss realized that it is also the Galois group of the field generated by the nth roots of unity. Gauss did not use this terminology, but essentially proved this theorem, which is still non-trivial even in these days, if one starts from basics. So let me go now to the next case, next interesting case of algebraic group, which are elliptic curves. What are elliptic curves? They can be defined by the equation that you see displayed is y squared equal to a cubic polynomial. This is an affine equation. We see it in the affine plane, but we must think to add a point at infinity in the projective plane. And which is not obvious at all by looking at the equation, there is a remarkable algebraic group law between the points of these of such curve. And this is expressed, it is the so-called chord and tangent process, apparently observed for the first time by Newton, I think. Anyway, it may be described as in the picture that you see. We take 2 points in the curve, we draw the line between the 2 points, we obtain a third point, and if we reflect the point with respect to the x-axis, we obtain the sum. So this is by no means obvious that this is a group law, but it turns out to be. So we may produce, out of 2 points, we produce a third point. And the important fact is that the coordinates of the new point are expressed with rational functions of the coordinates of the former points. This is why the group that we gain is an algebraic group. And from the analytic viewpoint, it is also very important, these curves the complex points of these curves are isomorphic to so-called complex torus. This is a quotient of the complex numbers, group of complex numbers by the lattice in the complex numbers. And there is also, similarly to what we had before with the usual exponential map, there is also here a so-called Weierstrass exponential map, which is a homomorphism. It is more complicated. I cannot describe in any detail, but there is an analog of the exponential map. And again, this Weierstrass exponential homomorphism transports the usual addition on C, the simple addition of complex numbers, into the group law that I have mentioned before, which is much more complicated to see in the between the points of the curve. But it comes from the addition. And now the situation is different with respect to the multiplicative group. We have m square elements of exponent m, more than before. Let me just recall some elliptic Galois results on torsion, which may be considered somewhat analog of what Gauss did. But now the situation is much more difficult. Why is it more difficult? One way is also because it depends on the coefficients of the equation. There are many elliptic curves. There is not a single one. And the Galois theory depends on those coefficients. So let me just mention a few landmark results. One is the Jean-Pierre Serre so-called open image theorem. It appeared already in the 70s. And we may say that it extends Gauss' achievements, but with more information, also to the elliptic case. It is a very difficult theorem still today. Another very important one is due to Barry Mazur, again in the 70s. He was able to find all the cases when the coefficients of the curve are rational numbers, all the cases when the torsion elements are expressed with rational coordinates. This is an extremely difficult theorem because it takes into account all elliptic curves with rational coefficient at the same time. The difficulty is this. It turns out that the torsion point with rational coordinates have never an order which is larger than 16. And for number fields, this was extended by Merel, and there is also work of others like Camiani and Perron. But Merel, let us say, in 1994, extended this to number fields different from the rational, which was quite a difficult, was not merely a translation and adaptation of Mazur's argument. New ideas were needed. So from elliptic curves, now we may go to a generalization of elliptic curves, which are the abelian varieties, so-called. They are the projective algebraic groups. And they are necessarily commutative. The name abelian does not come from the commutativity. It comes from the fact that Abel implicitly studied these objects. But they turn out to be commutative, so abelian in the commutative sense. And the elliptic curves are just the abelian varieties of dimension 1. But abelian varieties exist in any dimension. And a simple example is the power of an elliptic curve. This is very special. Other important abelian varieties arise as Jacobians, so-called Jacobians of curves, which we shall meet later. So the arithmetic is in the Galois structure. One may study in this case. It is even more difficult than the spatial elliptic case. And we may say it is not completely known even today, but much progress has been done due to the efforts of the mathematicians, some of which of whom I have listed. Bogomolov, Faltings. Faltings made a big step in this. Serre then used this. Then Masser-Wüstels did some transcendence theory, which also provided tools. And then Ken Ribet, Pink, Tamagawa, and Kadore made more recent progress on this, which I have not the time to recall. And now I have recalled something on individual torsion points in these algebraic groups. Now let me go nearer to the specific issues that I will speak about by looking at relations among torsion points. An old example comes from Gordon already in 1877. He studied the following equation: a sum of 3 cosines equal to -1. And the cosines, the point in this equation is that he studied when the angles of these cosines are rational multiples of pi. And this was not a random equation. The equation came from his study of finite subgroups of linear fractional transformation, and he found this equation by looking at eigenvalues somewhat. So he had a motivation for that equation. And this equation amounts to an algebraic relation among 3 roots of unity. It may be, if we use the cosine, we express the cosine as the sum of 2 roots of unity divided by 2 when the argument is a rational multiple of pi. And later, these kind of equations were studied by other authors, for instance, Mann in 1965, and John Orton Conway and Garrett Jones and Andrew Jones in 1976, in the setting of what they called, Conway and Jones called the topic trigonometric Diophantine equation, because you see, we studied rational solutions of these equations, but now not as usual in a polynomial equation as happens with the usual Diophantine equation, but in the trigonometric sense. And their results, let me just give a special case. They very easily proved as a corollary of their results that the only triangles with rational sides and angles which are rational multiples of pi are equilateral. And similar results also follow from their analysis for polygons with any given number of sides. If we specify the number of sides, their theory allows us to find a complete classification of the cases with these properties. And there are other applications which are listed here. I have chosen just a few until recently. Gross, Hironaka, McMullen to these topics. Coxeter polynomials, Bourgain, Gambert, and Sarnak to Markov surfaces, Kedlaev, Kolpakov, Poon, and Rubinstein to rational angles formed by vectors in the space, and also in joint work with Dvornicis and Veneziano to rational angles in plane lattices. So this, excuse me, it doesn't go ahead. Thank you very much. Okay, thank you. So independently, let me go now to speak of the conjecture of Lang. Independently of the above authors, Serge Lang had raised in the 60s a related problem of studying polynomial equations, so in 2 variables to start with. So polynomial equation f of theta zeta equals 0, but now the unknowns must be roots of unity of unrestricted exponent. So we want special solutions, and such a pair of theta zeta is a torsion point where it lies on the plane curve described by f by definition, and but we view this point inside the square of the multiplicative group. So the 2 coordinates are torsion themselves, and the pair is a torsion point. If the polynomial is given, we may ask, are there infinitely many such torsion points or not? It may happen that there are infinitely many, but as Lang expected, this can happen only if the polynomial has a very special factor, which must be a binomial that you may see written. And this was proved very quickly by Ihara, Serre, and Tate independently after the question asked them by Lang. So there is a special structure, otherwise we cannot have infinitely many points. And this result was later extended to arbitrary dimension. So not only for curves and not only in GM square, but in arbitrary dimension both of the ambient space and also of the algebraic variety. It was extended by Michel Laurent independently and Sarnak-Adams, and they proved, among other things, the so-called conjecture of Lang. This conjecture in particular predicted that an algebraic subvariety of the any power of the multiplicative group can have infinitely many torsion points only if it contains a so-called positive dimensional spatial subvariety, which in this case means it is an algebraic subgroup possibly translated by a torsion point. So there is an algebraic group structure explaining the infinitely many solution. This is the principle in Lang's conjecture. There cannot be infinitely many things by random. If there are infinitely many, there is an algebraic group inside which explains the reason. And these also had applications that I mentioned quickly. For instance, by Sarnak on Betti numbers of congruence groups. So quite different topics. Eilon Rudnick on greatest common divisors of the polynomials I have written. And until recently by Kurazov-Sarnak on crystalline measures. And the methods, I may say the Galois theory of Gauss is a precious tool, but there are other ingredients as one may expect. So let me go now for an analog of the conjecture of Lang, which actually came shortly before Lang and was formulated by Manning and Mumford in the 60s already. It was the following conjecture that a complex curve, we take a complex algebraic curve of genus at least 2. We may embed it in its Jacobian variety, which is an abelian variety. And they predicted that such a curve cannot have infinitely many torsion points. And this became a theorem already in the 80s. It was more difficult than the conjecture of Lang for the multiplicative group. This context of abelian varieties was more difficult. And several other proofs were then found by Serre, Coleman, Hindry, Bouillon, Roshovsky, Pink and Rösler, Matthew Baker, and Ribet. And still other proofs were provided later by Yuri Bilou and Lucien Spiro, Emmanuel Ulmo, and Shouvu Zhang for the abelian case. And these results were very important because they gave stronger results than the mere Manning-Mumford conjecture. And these proofs started to introduce the Galois equidistributions for torsion points. So when we take conjugates, the conjugates tend to go everywhere and tend to be equidistributed when the torsion order grows, and similarly for points of small height. And also a further proof was found in joint work of Pell and myself. Oh. Thank you. So this proof I mentioned because the methods relied on the Thank you. I hope it is, I have not done. So minimal structures, I will, if time allows. So these issues on torsion points may be extended to cover general group relations. Let me go quickly here for time reasons. So we may study not only torsion, but also relations involving the group structures. And the topic is called unlikely intersections. It was also came independently from other sources like Boris Zilber with motivations from logic, and Pink again had different motivations. And for instance, there is also the so-called André-Oort conjecture in this sense, which I skip for time reasons. We may see the André-Oort conjecture as an analog of the theorems of Manin-Mumford conjecture and Lang's conjecture, but for the context of Shimura varieties. We don't have now torsion points, but we have analogs, which are the analogs now are the complex multiplication points. So Pell applied the counting method to this context and achieved the result which went further than the results by André. And there were other steps, and the conjecture was finally settled by Zimmermann after steps of the people you may see written. So let me now go to torsion in families of algebraic groups. So we go a step further. We have now not a single torsion point and not a single algebraic group, but a whole family. The simplest case is the Legendre family of elliptic curves. You see, they are defined by the equation that you see displayed, plus the point at infinity, and there is a parameter lambda. Lambda is a parameter which varies, and for different lambdas, in general, you have different non-isomorphic curves. So one can have only 6 values of lambda which correspond to the same curve up to isomorphism. So in general, we obtain different curves if we vary lambda. And we may also consider families of points. You see just an example written there with the abscissa is constant 2, and the ordinate is just found by solving the equation. So we have a point for each value of lambda, and for each value of lambda, this point lies on the corresponding elliptic curve. And the choice of the sign is immaterial here. It may be shown that this P lambda, this family of points, they are not torsion identically. If we perform the group operation any fixed number of times, we don't find identically the identity. But if we specialize lambda, then the points become torsion for an infinite set, which is even dense. And this set consists of algebraic numbers. The torsion exponent grow, and these numbers have bounded Weil height, so they are dense, so they are many in a certain sense, but they are few in another sense, because, for instance, there are only finitely many rational ones or quadratic irrational ones, and so on. If we bound the degree, there are only finitely many. And we have Galois distribution, equidistribution in recent results by DeMarco and Madracchi for these numbers. Then Masser considered a second family of points. I have just written a specific family. Now the abscissa is lambda plus 1, and again we solve the equation for the ordinate. And so we have 2 families, which may be shown to be generically linearly independent with respect to the group law. And the values of lambda for which a single point becomes torsion is a sparse set. So this led Masser to ask a question, is the set of specialization for which both points become torsion even finite? Because it is difficult for each of those, but for each we may have infinitely many, but for both he asked this. Here the Galois group do not give enough information, but using the counting method and other tools, with Masser we succeeded in giving an affirmative answer, so to the finiteness. And later, this was extended to other families by in work, in particular, of the people that I have written. And these results may be seen somewhat as analogs of the Manning-Mumford conjecture, but relative, so in the sense of a family, not for an individual abelian variety, but for a family. And some other ones, there are also analogs in dynamics. So, and these were also recognized as special cases of conjectures of pink. So the method worked of a Q-bar, but with the Corvai and Masser, we succeeded in extending this by using the so-called Betty map, and I will skip this. Then let me conclude the last minutes by mentioning some applications to related topics. So we have, for instance, first the Pell equation, so-called Pell equation in polynomials. The Pell equation is the equation that you see displayed. It is associated of a d, and a d was classically an integer. In the equation was proposed, in fact, not by Pell, but by Fermat. And he sought not the rational solutions, but the integral solution, which is an important difference. And the equation turned out to be very important, apparently special, but linked with many deep issues in number theory, like class numbers, units, and so on. And there is also a polynomial analog, which was studied already by Abel in 1826 already. And now, in place of integers, we have polynomials. So D is a polynomial of even degree, and we seek solutions in polynomials. So from many viewpoints, the polynomials are analog of integers. We have, for instance, a Euclidean algorithm and many other analogies. In the polynomial case, however, if the coefficients are complex, it is generally unexpected to have solutions when the degree of D is at least 4. It can be proved using the former tool of the Betty map. The relevant polynomials are called Pellian. So the situation is different from the case of Fermat, when we have always solution as soon as D is positive and non-square. Now, there are no simple, necessary, and sufficient conditions in the polynomial case. And the issue is somewhat surprisingly linked with torsion. Now the torsion is in the Jacobian of the hyperelliptic curve associated to the discriminant D. And in joint work with Masser, we studied some families of polynomials, like the one that you see written. We have a polynomial of degree 2D. So the degree, let us think of fixing the degree and let lambda vary. So we obtain a one-parameter family of polynomials. We may ask, which of these polynomials are Pellian? Are they infinitely many or not? And for example, it turns out that for D equal 2, there are infinitely many values of lambda which produce a Pellian polynomial. But for D at least 3 or more, there are only finitely many ones. And for instance, we may check that lambda equals 0 lies in all these sets. We have an explicit solution. And an open question is, for instance, is the union of these finite sets, as the degree varies, is the union finite? Probably yes, but we have no proof. The Pell equation appeared also recently, studied by Kohler, for instance, in connection with decidability issues and the Hilbert-Stent problem in the case of function fields. Another related topic is integration in finite terms. What does it mean? It is related to the problem of expressing an indefinite integrals in terms of simple functions. This problem goes back to long ago and appeared among the first examples of differential algebra. A more recent view on these things, which are not unrelated, however, has been given to the study of algebraic relations among periods. So when do we have a relation between integrals of algebraic differentials, for instance? But now the integrals are definite integrals. This is a very deep and difficult topic raised by Grothendieck, and then Kontsiewicz and Zannier had an explicit formulation of some very attractive questions. So, and this is not completely unrelated, because when we have a formula for an indefinite integral, by specialization we may find some also relations among periods. And we call integrable in finite terms a differential whose integral can be expressed by a finite tower of operations, which are either of algebraic type or of exponential type or logarithmic type. This is a special type of operation, but it was the one of classical authors like Abel, Chebyshev, and then Ritt and others. So his research, the research of Abel, also involved elementary integration. And then there are also these authors like Liouville, Colchin. And more recently, James Davenport, the son of the famous number theorist Harold Davenport, investigated pencils of differentials to be integrated in finite terms. He sought to understand whether if the general member is not integrable in finite terms, then the same happens to the special members up to finitely many exceptions. This was his issue. And together with Masser, we produced an effective procedure to establish when this type of assertion is correct. And this involves torsion. This is why I mentioned this in this talk. By means of a certain criterion of Risch, the analysis involves torsion now in generalized Jacobians, which are related to Jacobians, but they involve also groups of additive or multiplicative type. Let me just state some special cases of the analysis. For instance, we may prove that there are only finitely many complex numbers, such that the integral that you can read may be found in an elementary way, so with the type of operation that I have mentioned. Only finitely many b. And there are someone. For instance, the spatial value of b equal to 1/2. You see, you have this formula. And the example says that there are only finitely many numbers for which we can have such a type of formula. So this is very special. And we have also a counterexample to what was the expectation of Davenport. So you see this differential written. It depends on a parameter lambda. This may be checked not to be identically integrable in finite terms. So its indefinite integral is not a simple function of the type I mentioned, but it becomes of the same type for infinitely many specialization. So this is an example which goes somewhat counterintuitive. And there is a curve, an elliptic curve underlying this, which has complex multiplication. And there is quite a long analysis that I skip, of course, which shows that complex multiplication plays a role. If there is no complex multiplication, then such examples cannot occur. So let me mention still another recent application to elliptical billiards. So work going back to Poncelet and Jacobi proves that to such a billiard with an elliptic table, one can associate an elliptic family of the shape that I have discussed previously. And in recent joint work with Corvaia, we applied some finiteness theorem to obtain finiteness theorems for periodic trajectories in such billiards. For instance, we have the following result. For each angle, if we fix an angle between 0 and pi, there are only finitely many periodic pairs of billiard shots from the same point in an elliptical billiard table, such that their directions form an angle alpha. So if we want that both trajectories are periodic and that the angle between them is fixed, we only find finitely many cases. This is not generally true for rectangular billiards, for instance. So let me conclude the talk by mentioning some open issues. One is to find some other cases of the conjectures of Pink and Zilber, which are related to torsion, as I stated, as I mentioned. And another open issue is to achieve effectivity in the counting of rational points appearing in some of the proofs. So effectivity means that in the finiteness theorems that I have stated, we want to find all the elements which the theorem states they are only finitely many, but the question is, of course, can we exhibit this finite set? And this was not known, but recently there has been progress by Beniamini, especially, and also to Gareth Jones and Harry Schmidt. And the issue is related to this theory of all minimality in model theory. So the effectivity is a very difficult issue, but it has a milder nature than in effectivity in other Diophantine contexts. And recently there has been big steps. And other steps has been done of the methods from all minimality have been developed by Kluckers-Comte for a Leuzer in the p-adic context. And they have been already applied by Chambert-Loire and Leuzer in 2017. So the context that I have mentioned concern complex numbers here in the p-adic context. And one expects here further applications of these p-adic results. So thank you very much, and I conclude here my lecture.